I know bonding is a long lesson, but it's fundamental. Do you know that this topic is foundation of a topic as far as like advanced organic chemistry? Well, it's worth it to learn about bonding because those are really easy marks, but very important about shapes and forces because it's foundation knowledge for many other topics in the future. So thank you for joining this lesson. Pay attention until the end and slowly go through it. My explanations, you can even skip through if you're confident that the timestamps are in descriptions anyway. This topic anyway is from AS Chemistry Crash Course. You can join the full course in the link in the description. And if you have any questions, comment down below. Hi there, and welcome to the second lesson of this course. Today we talk about bonding. We go through the definitions, we revise how to do dot and cross diagrams, shapes of molecule, intermolecular forces, and then we will link many topics together when we talk about bond strength. Let's get started. So at this point, you should have an idea of how the lesson works, some basic knowledge from GCSE that we can revise very briefly. We'll look at the objectives to have an idea of the things that we will cover in the most important concept. Then we will look at the content in many details and we will do some exercises together. But you will also have the end of topic exercises for you to do on your own and check with the solutions provided. At the end of this, you can assess your confidence on the topics that we did, looking at the checklist. Okay, so chemical bonding, the most important thing that we will look at are the definitions, because understanding the definition will help understanding many other factors in chemical reactions, reactivity, and so on. We will look at dot and cross diagrams. We will represent the type of crystal structures in all the type of bonds, as well as at the end looking at how the ionic radius and charge affect the bond strength, as well as the covalent bond, like the strength of the covalent bonds. In terms of intermolecular forces, we will look at the most important definitions, electronegativity, as well as the factors that affect their trends. We will look at polarity of the molecules, how intermolecular forces arise, and the consequence that they have on boiling point. And finally, we will look at the shapes of the molecules. So we will apply this VSPER theory, and we will look at the shapes, bond angles, and I will give you some tips on how to do it easy and how to remember it. Okay. The first thing before we start, remember metals and non-metals. What I need you to be able to do is predict the charges of an ionic compound, remembering that metals on the left-hand side, non-metals on the right-hand side. Remember, metals become positive ion, non-metal negative ions. Dot and cross diagram, well, what I want you to do for now, we will do a few examples, but important that you are confident with knowing that the group number tells us the number of electrons in the outer shell, and after knowing the electronic configuration, you know how to draw the electrons in that structure. Yeah, because remember that they always go one at a time and then they pair up. Predict charges of ions, applying the octet rule. Again, looking at the periodic table, I need you to be able to predict the charge because this will be fundamental to write formula of compounds. Let's start with ionic bond. Definition: all of the bonds are electrostatic attractions. So you can always remember these definitions and think about, so what is the positive and what is the negative component? Electrostatic attraction between the positive and the negative ions in the ionic crystal lattice. So oppositely charged ions. That's another alternative to say it. So that's important because knowing the definition will help you understanding what are the factors that affect the bond. We will get to that later. So how it's formed? Well, a metal transfer electrons to the non-metal to form a positive and a negative ion, respectively. So remember that the electrons are transferred from the metal to the non-metal. Look at magnesium; it needs to give away 2 electrons to have a full outer shell, so it will give these electrons to fluorine. The dot and cross diagram, when you need to write it, is just the outer electrons. Remember the brackets, the negative charge, and you must show that the electrons have been transferred. So look at fluorine that has 1 electron in a different symbol. Okay, because that comes from magnesium. So the transfer, you don't need to show it, you just need to be able to describe it. While the dot and cross diagram, yes, it's important that you're confident with that. And you write all the type of ions, because for this, well, the formula would be magnesium, let's see if I can write it, magnesium fluoride There are two fluorines, so you must show both of them in the dot and cross diagram. Otherwise, you won't get the mark. Let's look at the properties of ionic bond. So it's just a little summary because we will link the properties when we do the bond strength. But remember that they have high melting and boiling point because they exist in this giant ionic lattice, which is a large structure with many atoms, and there is a strong electrostatic attraction in all directions, as you can see from this ball and stick diagram. Even though it's not so representative of the bond, but it just shows that that is a lattice that has many atoms all bonded together. So they conduct electricity, but only when molten and dissolved. This is to do with the fact that molten and dissolved ionic compounds, they have free moving ions. So free moving ion means that the charges can move around, so they conduct electricity. And the other thing is that they're soluble in polar solvent. We will get to the polarity a little bit later, but it's because these positive ions, positive and negative ions, can be taken, they're taken apart when a solvent like water surrounds them. And we will see a bit what this polarity means a bit later. So this is a worked example on how we could be asked to describe the bond. Explain in terms of electron how lithium sulfide is formed from its atoms. The marks. Two lithium atoms lose one electron each. One sulfur atom gains both or two electrons, forming two Li plus and one S2 minus. So the explanation, remember that the marks are always given for the gain, loss of electrons, or you can mention it as a transfer, and then the charge of the ions. Easy marks to get. Let's go into the next bonding. So metallic is an electrostatic attraction between the positive metal ions and the localized electrons. It's formed because the outer orbitals of metals, they merge to form a sea of the localized electrons. That's why we have a positive metal ion. They lose the electrons, but they lose it in this structure. That's why it's nice to think as the orbitals, they merge. This is important for the properties because they have high melting and boiling point, because again, we see, as you can see, a regular arrangement of many ions. They conduct electricity because they have delocalized electrons. They're malleable and ductile because notice that they're stuck into layers. When we talk about one pure metal alloys that are a mixture of metal, it's a bit different. Malleable because the layers can slide along each other. Ductile, they can be bent into shape because as forces applied, those layers disrupt. Okay, alloys, they disrupt this layer because if you think about, we have one small metal, one big metal, and those layers they get disrupted. So they have different properties. They're not malleable and ductile as much. And again, the structure giant metallic. One thing to summarize, the conductivity. So we've seen two reasons. One is that they must have delocalized electrons or free moving ions. Those are the only two reasons why substances conduct electricity. And that's important for the next bond that we see. First, let's look at how it's formed. So covalent bond, again, is an electrostatic attraction. This time is between the positive nuclei and the shared pair of electrons. It's formed because the outer orbitals of non-metal, they overlap, and they can share one or more pair of electrons. So one pair of electron would be one single bond. More pair of electrons could be double or triple bond, like in this example. Or we can have also a slightly different way to another bond that we will see in a moment. I want you to notice how this dot and cross diagram has been done, because if you're not sure about how the atoms bonded together, draw their dot and cross diagram separately. And then you know that one covalent bond is simply made by joining those two electrons, so you know how many bonds it will form. Like in this case, this little line represents that fact that each oxygen shares one electron with carbon. And notice that there will be two pair of electrons shared between each atom, and this results in a double bond. Remember that this is represented as a line, so if it's double, there will be two lines. This is so important for the shapes. So be confident in drawing dot and cross diagram, but we will do some examples. There is another bond that is covalent that we'll come across a lot next year in year 13 when we talk about transition metals. And this is called the dative covalent bond. So the outer orbitals of non-metals overlap and they share one pair of electrons. The difference is that the pair of electrons come from just one atom. This is important so much in understanding reactivity of some organic molecules, because look, this is ammonia. We know that ammonia is a base. Why it's a base? Because it's a proton acceptor. Why a proton? Because it has an empty shell. So hydrogen, when it loses its electron, it remains as one single proton in the nucleus. So it has this positive charge, which means that it can accept 2 electrons to have a full outer shell. And ammonia has a lone pair of electrons, so it can fully donate that, which means that proton acceptor, they're likely to have a lone pair, which means that they're likely to form a dative covalent bond. Okay, so this is just to mention that this is important, because we will see it in many other topics, and it will explain reactivity and bonding. Let's look at the properties. So those that we've seen so far, carbon dioxide, ammonia, they're all small molecules. Other example, water, methane, even diatomic elements like nitrogen, oxygen, fluorine. They're small molecules, so they're covalently bonded because they're non-metals, but they have these properties: low melting and boiling point, not conductive, not soluble. Low melting and boiling point is due to the intermolecular forces. We will mention that in a moment. Non-conductive because there are no free-moving ion and no delocalized electrons. Not soluble in water because there are no ions that can be pulled apart. Okay, some could be soluble, but that depends on the intermolecular forces. So we will explain that a little bit later. There are some giant structures as well when we talk about covalent bonding. So giant structures, just like all the other structure we've seen, they have high melting and boiling point, because when we change physical state, we're actually breaking that strong bond. They're conductive only if the localized electrons are present. They're not soluble in water generally. And they're called a giant molecular structure because they're covalently bonded. So we're talking about molecules. Do you recognize this structure? I hope you do, because this is graphite and this is diamond. So giant structures are not many examples, but carbon is the main one, and all its allotropes. We've seen graphite, we've seen graphite, a single layer of graphite. Diamond is another one. There are some others that you need to know. We will come across them in the topic of periodicity. And because silicon is in the same group as carbon, it also bonds in a similar way. In fact, the silicon dioxide, it's another example of giant molecular lattice. Okay, so it's important to remember the difference between giant structure and the small molecules, because a small molecule can also be big. Think about what you studied in GCSE, fullerene. It's C60, this ball shape with all of it's like hexagon, all bonded together to form a spherical shape. It's still a small molecule, so the boiling point would still be low. Yeah, even though there are so many atoms that are bonded. Another example would be sulfur. Sulfur exists as S8. Still, it's a small molecule, but it's pretty large because there are 8 atoms all bonded together. Okay, but small molecule, it's always a limited a number that we can kind of count. While giant structure, there are many, many atoms bonded together, yeah, and the properties will be completely different. One last thing, graphite. Notice that carbon is bonded to 3 other carbons, which means there is 1 spare electron for each carbon. This means that there are free moving electrons. So delocalized electron means it can conduct electricity. So it's really important to link the bonding to the properties of the molecule in case you would have to do some interpretation question. So this is the end of the first part. I will leave to you the practice questions because you have solutions that you can check on your own, and we will go into the next part, which is the intermolecular forces. Okay, so far it might have been easy, just a revision on bonding. But one thing that I really want you to learn, and here is the link to the video on the bonus about bond strength. You need to fully understand the factors that affect the strength of these bonds, because you will have to apply this concept in exam questions, but also to understand the concept of advanced physical chemistry, like different in enthalpies and so on. So it's worth it to have a look at this video. I'll put it in the description. Otherwise, just stay here and enjoy the second part of the lesson, which is forces. In the second part of the lesson, we talk about intermolecular forces. So before we understand how they arise and the consequence that they have on properties, we really needed to look at one very important property, that is electronegativity. So as a definition, is the ability of an atom to attract electrons in a covalent bond towards itself. But let's think why they attract electrons toward itself. The most important thing to understand is the nuclear attraction. So every nucleus has a positive charge because of the protons. However, the attraction that this nucleus has on the electrons is determined not only by the number of protons, but also of how many shells are present around this nucleus. The more shells are present, the further away is this nucleus. So the electrons that are at the very far end that are shared with another atoms, they won't be as attracted. Okay, what I'm trying to say is that the shielding, this is the effect that it's called, affects the electronegativity, because the further away, let me draw here a simple diagram to show that. So if we have a nucleus and those are the electrons shared, and let's say that we have another atom that is sharing electron, but now it's this big. Maybe you don't see that. Well, anyway, maybe it's this big. The electrons are going to be a lot more attracted by that nucleus that it's closer. While the nucleus, if it's further away, like in this case, they're not going to be so attracted. So I really wanted to understand this diagram because the trend in electronegativity depends on that. And this effect is called nuclear attraction. So it's how much the nucleus would attract electrons. And in this case, we're talking about the electrons that are shared in a covalent bond. Notice the trend. So the general trend is an increase across a period and decrease down the group. Exactly for that. And we will see that a lot in periodicity. So this is just the first touch on this concept. So we'll go into more detail with many diagrams then. But notice that from lithium to fluorine, the electronegativity increases. The reason is that there is an increase in nuclear charge because there are more protons. And the electrons are added onto the same shell, which means that they're not further away. They're at the same distance, but the nucleus now it's more positive. So those electrons will be more attracted. That's why the electronegativity increases, and that's why fluorine is the most electronegative. As we go down the group, the electronegativity decreases. Because if you think about the nucleus, and if you think about the electrons that are shared, they're always further away from that nucleus, because as we go down the group, there are more full shells, which means that, visualize that, the nucleus, it's further away from that shared pair of electrons, so it's going to be less attracted. Okay. The electronegativity, well, we can always work out this trend because we will have a full understanding of this concept of nuclear attraction, but it's also defined numerically by this Pauli scale. So you might be given that in the data sheet. Otherwise, it's important to understand the trend so you can always work out if there is a difference in electronegativity. This is because a difference in electronegativity results in polar bonds with partial charges. So the first thing to think about is that forget about the electron just as being those dots and crosses, but electrons, they are present in orbitals, region of spaces where electrons are likely to be found. So start to think as electrons in terms of clouds, okay? So if we look at this example in colored, so these are HCl, chlorine is more electronegative than hydrogen. So what this means is that all of the electrons in this bond, they will be drawn closer to the chlorine. So this results in more electrons being present on one side of the molecule and less electrons on the other side. And this results in these that are called partial charges. Okay, so partial charges because it's not like an ionic bond that the electrons are fully gained or lost, but the electrons are just a little bit closer to that side. A little bit more electrons on that side means partial charge. Okay, while a nonpolar, notice that there is an even distribution of electrons. Like if we have two elements that are exactly the same, they don't have a difference in electronegativity, so they're going to be nonpolar. There is another case though, because not all molecules with polar bonds are polar. And this is to do with the symmetry, because in symmetric molecules, the dipoles cancel out, so the molecules are nonpolar. So think it in terms of electron cloud. Let me see if I can use a highlighter. So notice in this molecule, the the electron density, those electrons move towards the chlorine, and that's shown with an arrow with that little sidebar here. It goes in the direction of the chlorine because chlorine is more electronegative than carbon and hydrogen. So all of the electrons move on this side of the molecule. And that's why there is going to be a dipole, a net dipole, because the electrons, they move all in one direction. But in this case, notice how in the carbon chlorine, the electrons, they go in opposite direction all away. And this means that they will cancel out. And because there are four, actually, they all cancel out. So there is no dipole. Okay, we will look at some other examples. In fact, this is your turn. So I would like you to press pause and then press play again when you're ready. But first, I would like you to try. If you're ready, let's do this together. So we need to predict how which of the following molecule does not have a dipole moment. The key thing will be to draw them out. And this will become easier when you get a bit more confident with the shape of the molecule, if you're not already, because we need to draw them out. So we're talking about carbon with 4 bonds. So we know that this is going to be the shape always. And this is, we will see it in a moment, but it's tetrahedral shape. So it's like this. I would suggest you to learn how to draw the three-dimensional structure because this helps in looking at the direction. So if we look at the first one, notice that we have hydrogen, chlorine, chlorine, and chlorine. So the direction of the electron density is towards the chlorine because we know that that's more electronegative than carbon from its position in the periodic table or from the scale that we have, which means that notice that all of the arrows go in one direction, so this will be polar. Let's look at the other one. So let me see if I can erase this. Okay. So now we have 2 chlorine that are present and just 1 hydrogen. So let's see how that would affect. Well, the way is always to do the electron density. Notice that again, they go in the same direction, so it will be polar. And probably you're starting to understand. The other one also has another chlorine added to that. So the dipole go in the same direction, so it will also be polar. So the only one that is not polar is the CCl4, because all of the dipoles, they go all in different directions, so they cancel out. So this one is not polar. Here there is another question. So if you have a bit of understanding of and previous knowledge of organic chemistry, do that. Otherwise, we'll do it after you've covered organic chemistry. If not, press pause, try it, and then when you're ready, press play and we do it together. If you're ready, so this molecule, those 2 molecules, they are alkenes. Alkenes, E and Z, because there are isomers, so we have carbon with 4 bonds as an alkene. Keep in mind the shape, we will look at that later. But there are 2 hydrogens and 2 chlorines. So the E means that the priority groups are on opposite side, and those are the chlorine because they have a higher mass. So the chlorine will be on opposite side, and this is our E. The Z, the groups are on the same side. So let's have a look at the direction of the dipole. So we know that the electron density moved towards the chlorine because that's more electronegative. So in both molecules, this is the case. Notice the direction. So in the E, they go on opposite side. They cancel out. In Z, they go on the same side. So if you think about electron density, there is more electron density on this side of the molecule, which means that the only one with the dipole will be the Z. Okay. So this is all for polarity, and this is what will help us understanding the intermolecular forces. The first force to talk about is London dispersion force. It's also called van der Waals or induced dipole. So it arises because of an uneven distribution of electrons. Let's think about what that means before we go further. So as I said, electrons, So imagine them as a cloud, and this cloud is around the molecule and it's constantly moving. Okay. At one point in time, all of these electrons will be on one side of the molecule. So electrons are negative. So this uneven distribution causes one part of the molecule to be more negative and the other one to be more positive. The consequence of that is a temporary dipole because it's for one moment in time. This temporary dipole will induce to the neighboring molecule a dipole, the opposite one, of course, because otherwise too many electrons would repel. So this temporary dipole induces a dipole in the adjacent molecule. The more electrons there are, the stronger the force because there are, and remember, those electrons are moving around. So the more electrons there are in a molecule, the stronger this London dispersion force. So temporary dipole induces a dipole in an adjacent molecule. So the important thing to remember is that all of the molecules have this force, and that the bigger the molecule, the stronger the force, because this depends on the number of electrons. But another thing is also how many points of contacts are present. So if molecules cannot get close, they won't have a strong force. But if the molecules can get very close, then they would have a stronger force. And here I'm linking to some properties of organic chemistry, which we will see then. Okay, just to mention it once. Let's go in the second force. Dipole-dipole interaction, also called a permanent dipole. This one arises due to a difference in electronegativity between atoms and forms a permanent dipole. But this is only between polar molecules. And of course, the more polar the bond, the stronger the force. So remember that it's represented always as a dashed line between dipoles. And the dipoles, you can determine them from the periodic table and from your knowledge in difference in electronegativity. So an example, HCl, hydrogen, is less electronegative than chlorine. So chlorine would have a negative dipole because the electron density moved towards it. And this will attract the positive dipole of another adjacent molecule. So only polar molecule, the more polar, the stronger the force. A special type of dipole-dipole or permanent dipole, it's hydrogen bond. It's actually the same as if you notice, it arises due to a difference in electronegativity between atoms, forms a permanent dipole, but this is only between nitrogen, oxygen, and fluorine that are bonded to hydrogen. Can you guess why? If we think about the difference in electronegativity, notice that nitrogen, oxygen, and fluorine are right at the top of the periodic table and where the electronegativity is the highest. So the most electronegative element, nitrogen, oxygen, or fluorine, hydrogen is one of the least, which means that the dipole will be so different that this will have a bigger impact on the properties of the molecule. Be familiar on how to draw the hydrogen bond. That's really, really important because that always arises from the lone pair of an atom, in this case oxygen, to the positive dipole of the hydrogen. Okay, and hydrogen water has so many special properties because of this force. Okay, so be familiar and practice how to draw this out. And now we will look at how at these intermolecular forces. The key thing, the biggest effect that these forces have is on the boiling point. This is because the stronger the intermolecular forces, the more energy is required to break it. Therefore, higher boiling point or melting point of a molecule. Okay, so this is a classic example. Predict which molecule has the highest boiling point. I will help you a bit on how to approach this. It could be multiple choice, could be an explanation question. The important thing is that you think about all the forces that are present in each molecule, so you could list them out. Okay, if you want to give it a go, pause. Otherwise, follow along with me. So HCl, what molecule does it have? What force does it have? For sure, it has London dispersion force. But then we need to think, does it have is there a difference in electronegativity between hydrogen and chlorine? Yes, there is. So it's also going to have I'm going to call it dipole-dipole force. Next one, HF, what does it have? For sure, London dispersion force. What else does it have? Oh, hydrogen and fluorine. We need to remember that this is hydrogen bond. Remember, just fluorine, nitrogen, and oxygen. So it has hydrogen bond. Then this one, what does it have? Of course, London dispersion force. Then we have one carbon-chlorine bond, so this is going to be dipole-dipole. And this situates 5 carbon and hydrogen. That's something to know, but also we could predict it from the poly values. It does not, there is no difference in electronegativity, which means that the only force is London dispersion force. So HF is the one with the strongest force, which means that it's going to have the highest boiling point. Okay. Then if we want to compare other molecules, for example, those two, we will need to think about the biggest difference in electronegativity, or, but it's the same because it's chlorine, London dispersion force. So actually this one will be the second with the highest boiling point because it has a stronger London dispersion force compared to HCl, right? Because there is carbon with more hydrogens, and this is a smaller molecule. So if the forces are the same, we will need to think about the factors that affect these forces. Okay, so I will put some extra material about the application of intermolecular forces and some more complex exam-style questions. But for this lesson, that is it for the intermolecular forces. To the next part, which is the shapes. Let's talk about shapes of molecules, specifically shapes of covalent molecules. So there are two different categories of shapes that we need to remember. Some are called regular structures and the others are irregular structure. So we need to understand a bit what it means, this regular structure. Regular means that they don't have a lone pair of electrons because this will disrupt the bond angle. Let's think about why. So first of all, there is an equal repulsion between bonded pairs. So they arrange themselves as far as possible to minimize the repulsion. So there are no lone pairs and they arrange themselves as far as possible. And the following here are the regular structures to know. So linear, no, of course, there are just 2 bonds. So those are as far as possible. That's 180. And remember the bond pairs, well, they're made of electrons. That's why they repel. Trigonoplanar is like a plane of 360 divided into 3. Tetrahedral, because it's 3-dimensional, so they arrange themselves with this angle of 109.5, and this is the one really to remember. Trigonal bipyramidal, notice that we have a plane with as a trigonal planar, and then one bond at the top and one at the bottom. Octahedral, also one at the top and one at the bottom, because those are the one that are the far apart. And then there are 4 bonds into the horizontal plane. And here you have also some examples. But now let's talk about what happens if we have irregular structures. So the first thing is to understand this theory called VSPER theory, which is valence shell electron pair repulsion theory. Why? Because lone pairs cause a greater repulsion, while the bonded pairs get closer together. So this is the order of repulsion, and this will affect the bond angle. So lone pair to lone pair is the biggest repulsion. Lone pair to bond pair. Second, bond pair to bond pair is the least repulsion. So when there are lone pair, the bond pair will get close together by a specific value. So let's look at the examples. The important thing to remember is the change in angle. So we'll get that to a moment. So anyway, those are the most common one. Notice how both of these, they're similar to the tetrahedral because they have 4 things around. So lone pair and 3 bonded pair. And the angle of the tetrahedral was 109.5. Let me highlight it here. So it was 109.5. But notice the 107 for one lone pair, 104.5 for the 2 lone pairs. Those numbers are not random. In fact, we will do an example together. But the thing to remember are the name of the shape depends on the number of bonds. So linear, nonlinear for 2 bonds, trigonal for 3 bonds. The bond angle is derived from the regular structure. And so we need to get the angle of the regular structure, and each lone pair would increase the repulsion and decrease the bond angle by 2.5. So let's see how we can apply this. Let's do this example together. If you want to give it a go, do that. Otherwise, we'll do it together. First of all, we need to. So if we need to find the shape, and we need to think about, I need to know how many electrons are present. And I think the best way is always to get the dot and cross diagram. Okay, so you can do that, or you can count the total number of electrons. That's also okay. So there are always two ways. So sulfur has 6 electrons in the outer shell. So we can draw like this. Remember how I draw them out as one on each side and then they pair up. And chlorine has 7. So we know that it's able to share just 1. So this will be our dot and cross diagram. So this tells us, I missed one. This tells us that there are 4 regions that we need to consider. But in those, 2 are lone pairs and 2 are bonded pairs. So because there are 4 regions, which regular structure do we take in mind? The one with 4 things, the tetrahedral. So it's important to keep it in mind. So we could write it here on the side. Okay, so we're looking at the tetrahedral that has an angle of 109.5. However, there are 2 lone pairs, and we know that each lone pair decreases the angle by 2.5, which means that in this structure, we could get, so for example, let's say that those 2, they're not bonded pair anymore, but they become lone pair. We would draw it like this. And the angle would decrease by 2.5, but twice that. So we would get an angle of 104.5. In terms of name, 2 bonds. So it would be, remember the name derives from the number of bonds. That's linear, but of course it's non-linear because it's distorted. So it will be a non-linear. So try to apply these 3 steps on how to find the name and the angle to a bit more complex, but you have a series of practice questions with solution for you to try to do it, to bring all of these topics together. Otherwise, go to the extra video to get more practice of these shapes of covalent molecules.